Hello everyone, welcome back to this online class. Today we are going to look at how to solve second order linear homogeneous ODEs with the constant coefficients. Now we are given three questions. In part A, we have d squared y dx squared minus dy dx is equals to 0. In part B, we have d squared y over dx squared minus 2 dy dx plus y is equals to 0. And in part C, we have d squared y over dx squared minus 6 dy dx plus 25y is equals to 0, subject to the conditions, the initial conditions, that when x is 0, y is equals to negative 3, and also when x is 0, y prime is equals to negative 1. So we need to find the solutions of those three ODEs. They are homogeneous. Remember, even before we look at how to solve each of them, I want us to take note that let's consider this equation. A d squared y dx squared plus b dy dx plus c times y is equals to a function f of x. Now, this equation is said to be homogeneous if f of x is equals to 0. So you can say if that function f of x is equals to 0, then we say the ODE is homogeneous. ODE is homogeneous. Another one, if A, B, and C are not functions of y, comma, then the ODE is linear. Of course, the order is 2 because the highest derivative in the equation is 2. So the order is 2 and the degree is 1. The power of the highest derivative is 1. So the 2 here is the order, and this is raised to power 1. So the 1 there is the degree. So now this equation is of order 2. Order is equals to 2. Degree is equals to 1. Now, there's also what you call dependent variable. In this case, y is the dependent variable, while x is the independent variable. So also take note that y is called dependent variable. X is called independent variable. So we have said when the right-hand side is 0, then the equation is homogeneous. What about if the right-hand side is not equal to 0? Then we say that the equation is non-homogeneous. So having talked of the general form of a second order ODE, and having explained what we mean by homogeneous, linear, order, and even the degree of that equation, let's now answer the questions. In part A, we have d squared y over dx squared minus dy over dx is equals to 0. So you write here part A, d squared y over dx squared minus dy over dx is equals to 0. I am going to write this equation in terms of the d operator. So you say let d, this is a differential operator, to be derivative with respect to x. So that this means that if I square both sides, I'm going to get d squared is equals to the second derivative with respect to x twice. So now the equation can now be written in terms of the d operator. Let me show you how to express that in terms of the d operator. So this derivative will now be d squared operating on y. Then the other derivative is simply d operating on y to give us 0. And when you look at the left-hand side, you realize that y is common. So that can be factored out so that we have d squared minus d. This is an operator operating on the function y to give us 0. So to solve this equation, we need a non-trivial solution. Non-trivial means that the solution where y is not equal to 0. This is a non-trivial solution. Let me write here. Non-trivial solution. That is the solution that we need. Now, that solution depends on the roots of what we call the characteristic equation. And to get the characteristic equation for this equation, you can write auxiliary equation stroke subsidiary stroke characteristic. They mean the same thing. To get that, you equate the coefficient of y to 0. So d squared minus d is equals to 0. Of which this can be written as, if I factorize d, then d minus 1 is equals to 0. So we said that the non-trivial solution that we need depends on the roots of the auxiliary equation. So let's find the roots of that equation. Of course, there are two roots. Of course, you know either d is 0, or d minus 1 is equals to 0. So this means that the first root d1 is equals to 0. The second root d2 is equals to 1. 0 and 1 are real numbers. So these are real and distinct roots. The roots are real and distinct. So then how do you write your general solution when you have the roots to be real and distinct? Remember, if I say let this be alpha and this one is beta, our general solution is y is equals to a constant c1 exponential alpha x plus another constant c2 exponential beta x. Our alpha is 0 and our beta is 1, so we can replace them there. So this can also be written as c1 exponential 0 x, which is just 0, plus c2 exponential 1x, which is just x. 1x is just x. Anything raised to 0 is 1. So this is the same as writing c1 plus a constant c2 exponential x. So we can just say, or y is equals to that one. So this is our general solution where c1 and c2 are arbitrary constants. So this is general solution. C1 and C2 are arbitrary constants, which we can determine their values if we are given some initial conditions. Let's answer part B. In part B, we have d squared y over dx squared minus 2 dy dx plus y is equals to 0. So again, write this in terms of the d operator. So this will be, of course, I've shown you how to define our d operator. So in terms of the d operator, this can be written as d squared y minus 2 dy is the other term, then plus y is equals to 0. You see y is common on the left hand side, so that can be factored out so that we have d squared minus 2d plus 1 operating on y to give us 0. So the auxiliary equation equate the coefficient of y to 0, so we'll have d squared minus 2d plus 1 is equals to 0. And you can factorize. If you factorize that, this is the same as d minus 1 squared. Now d minus 1 times another d minus 1 is equals to 0. So what about the roots? There are two roots and they are equal. So the first root is the same as the second root, and we are getting a real number, which is 1. So the roots are real and equal. Real equal. Those roots are real and equal. D1 is equals to D2, which is equals to 1. So in that case, let's say this is our alpha. Let's say D1 is equals to D2, and you're getting alpha. So how do you need to write your general solution? You'll write y is equals to a constant C1 x plus another constant C2, then exponential alpha x. That's how you need to write your general solution. In this case, our alpha is 1, so I'll just replace the value of alpha. So you can just say for y is equals to C1x plus C2 exponential 1x, which is just exponential x, because alpha is 1. So that is our general solution, where C1 and C2 are arbitrary constants, which you can determine their values if you're given some initial conditions to apply. Lastly, in part C, we are given this ODE, d squared y dx squared minus 6 dy dx plus 25y is equals to 0. The conditions are y of 0 is equals to negative 3, and the other one, y prime 0, is equals to negative 1. So again, let's write this in terms of the d operator. So this can be written as d squared y, then minus 6 dy plus 25y is equals to 0. So I can see y is common on the left-hand side. So let's factor out y so that we have d squared minus 6d plus 25, and then the y is common. On the right-hand side, we have 0. Remember, the function must be written to the right of the operator, because an operator operates on a function. Don't write y on the left. Start with the operator, then followed by the function. Now, the auxiliary equation. Auxiliary equation. It is d squared minus 6d plus 25 is equals to 0. Let us find the roots. Is it possible to factorize? No. So let's use quadratic formula. If you cannot factorize, go for quadratic formula. So in this case, we'll find two roots, yes. So the first and the second is equals to a negative of negative 6, that's negative b. Remember quadratic formula that d is equals to negative b plus or minus the square root of b squared minus 4ac, everything over 2a. This is what I'm calling the quadratic formula, where a is the coefficient of d squared, b is the coefficient of d, and c is the constant term. What we are solving is ad squared plus bd plus c is equals to 0. So to solve it, that's how you need to get your roots. So negative of negative b, come back here, then plus or minus the square root of negative 6 squared minus 4 times a is 1, our c is 25, everything over 2 times a, 2 times 1. So what is this equal to? 6 plus or minus, that's 36 minus 100. That's the root of 36 minus 100 over 2. You see 36 minus 100 is the same as negative 64, and the root of negative 64 is a complex number. So this is the same as 6 plus or minus the square root of negative 64 over 2, and this can be written as 6 plus or minus iota times 8 over 2, which is the same as 3 plus or minus iota times 4. What I'm calling iota, the iota here is the same as the square root of negative 1. So these are complex conjugate roots. So let's say this is alpha, and this other one is beta. Remember, the roots are complex conjugates. Complex conjugates. D1 is 3 plus I4 and D2 is 3 minus I4. Those are the two roots. They are complex conjugates. Now, how do you write your general solution? You can say that therefore, y is equals to exponential alpha x times a constant C1 cosine of beta x plus another constant C2 sine of beta x. That's how you need to write your general solution. Now, where there is alpha, we put 3, and where there is beta, we put 4. So when you make the substitutions, you say, or y is equals to exponential 3x times C1 cosine of 4x plus C2 sine of 4x, where C1 and C2 are arbitrary constants. So this one here is our general solution. general solution. Now, you see we are given some conditions to apply, the initial conditions. Now, to get the particular solution, let's apply the initial conditions. First of all, let's start with the first one, apply. We are told that y at 0 is equals to -3. So I'm going to apply it in this equation that you substitute. This means that put x is equals to 0 and y is equals to -3. So what are we going to get? It will be -3 is equals to exponential 0 c1 cos 0 plus c2 sine 0. And you know sine 0 is 0, so this one will vanish. And anything raised to 0 is 1. So this simply means that -3 is equals to c1, because cosine of 0 is 1. Cosine of 0 is 1, and exponential 0 is also 1. So we only remain with c2 is equals to, c1 is equals to -3. So let me replace it back. Now we have found c1. Now we need to apply the other condition. Before I replace c1, we need to apply the other condition that has the derivative of y. So I need to find dy dx for this one. So take note, if I differentiate, I get y prime is equals to, y prime is the same as dy dx. That is equals to exponential 3x, that's constant, then differentiate c1 cos 4x, that is -4c1 sine 4x plus 4c2 cos 4x. I'm using product rule, plus now 3 exponential 3x, then retain the other function, that is c1 cos 4x plus c2 sine 4x. If I simplify, it's the same as exponential 3x. Let's combine the cos. I can see 4c2 cos 4x and 3c1. So it is 4, let me start with c1. 3c1 plus 4c2. That is cos 4x. What about sine? I can see here plus -4c1 plus 3c2 sine 4x. So now apply the other condition that y prime at 0 is equals to -1. So what does it mean? That I'm going to substitute x is equals to 0 and y prime is equals to -1. So therefore, it means -1 is equals to exponential 0. Remember, x is 0. Then here we have 3c1 plus 4c2 cos 0, then plus -4c1 plus 3c2 sine 0. Where we have sine 0, that the whole of that term will vanish because of the sine 0. So this is 0. And you know cos 0 is 1 and exponential 0 is also 1. So you write or -1 is equals to 3c1 plus 4c2. But what did we get as c1? c1 is -3. So this means that -1 is equals to 3 times -3. That's what we got as c1. plus 4C2. And so you can now make C2 the subject. So this is -1 plus 9. That's -8. Then you divide by 4. -8/4. That should give you -2. So what we have found there is the value of C2. And now we now know the values of those two arbitrary constants. So if you replace them in the general solution, you obtain what is called the particular solution. So you can just say that hence, you write here hence, our particular solution is now y is equals to exponential 3x. C1 there was -3 cosine of 4x, and our C2 is -2 sine of 4x. So I have replaced the values of C1 and C2. There's something that you have left out. Look at where we are finding C2. Here, if you make C2 the subject, you see this is -9. If I take it here, it will be +9. So +9 minus 1 is +8. So C2 should be +2, not -2. So change this, should be +2. Instead of -2, it should be +2. So this is our particular solution. So let me comment on it. You write here, particular solution. Now that's how to solve homogeneous ODEs of the second order and linear with the constant coefficients. So thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. If you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems in homogeneous ODEs of the second order with constant coefficients and also linear. Bye-bye.